All right, so last little thing here we're going to talk about is local linearity and existence of derivatives and what would cause a derivative to not exist. So we remember our instantaneous rate of change formula. F prime of x is the limit as h approaches 0 of f of x plus h minus f of x all over h. So let's explore what happens with the absolute value of x. So there are two ways of doing this. Let me actually do it the easiest way, right? Because I don't think anyone really cares about those, other than me and maybe like one or two other students. So we saw that the absolute value of x was a piecewise function. It was negative x whenever x was less than 0, and it was positive x whenever x was greater than or equal to 0. And we know that that gives us the familiar V-shape equation, shape, line, function. There we go. And so here's our absolute value. So again, derivatives are a linear operator. So if I took the derivative of both sides, this is like saying the derivative of the absolute value of x is equal to the derivative, let me actually move this down a little bit, of negative x, but only when x is less than 0 or equal to the derivative of positive x, but only when x is greater than or equal to 0. So we know that the derivative of negative x, right? So negative x is a line with a slope of -1. This should be -1. The derivative of x is just equal to 1. So if I graph my derivative, I'm going to get something that looks like this. Doesn't matter where you put the open or the closed dot. So we can kind of see here that as we're approaching 0, our derivative has this jump in it. And this is a problem, right? Because, well, if I look at the limit as we approach 0 from the left and the right of the derivative, it doesn't match. What would happen if I did this way, right? I'll leave this up to you if you're bored later on. We'd have the absolute value of x plus h minus the absolute value of x all over h. So again, when we look at this from both directions, this does not exist because we can, again, kind of see that from the left and the right, we have this jump, right? So this limit is undefined. So that creates a problem for a derivative, right? So this type of problem, when we have a jump in our derivative, is called a corner. So we would say that the absolute value of x has a corner when x is equal to 0. And again, the reason is because our derivative has a jump, right? The limit doesn't match from both sides in our derivative, our instantaneous rate of change. Put another way, right? It says that we're decreasing at a constant rate of 1, and then we get here and boom, we have an increase of 1. I hope it didn't scare you. So that's kind of like the problem with our limit. So we can also look at this visually as well. So you can see whether or not a function has a derivative if we apply what's called local linearity. Right, so here's my function, right? Here's local linearity. The idea behind local linearity is that if you zoom in around a spot, you should always see a line because, again, we should be seeing a tangent line to the function. So if I were to zoom in, say here, right, I can zoom in and all I see is a line for my function. The problem, and I suggest that you do this, right? Because if I do it, you might think that I'm like lying or something. If I zoom in around 0, so I'm zooming in around 0, hard to do it, but trying to zoom in around 0. Maybe I should say it doesn't come with me. Just keeping the plus button. It's like this is the first time I've ever used Desmos. Right, so if I keep zooming in, I don't ever see anything other than that kind of like corner in this function. Right, so I can't zoom in enough that I never lose that corner, right? I'm already at 5 to the -12th, so like a trillionth or a billionth or something, and I still see that corner of our absolute value, right? So we would say that this absolute value function does not have local linearity. I can't zoom in and turn it into a line. Now, we could change this function, right, to see something that does have local linearity. So suppose I looked at y equals x cubed plus 1, and I want to zoom in around x is equal to 2, according to the question. Right, so x cubed plus 1 would look like this. and 2, right? So we would have 2 and what's that going to be like 9? 2, 9. So I want to zoom in around that point 2, 9. All right, so let me plug this in. Let me get rid of that. So y equals x cubed plus 1. And we have the point 2, 9 on it. And so there's a point. But so if I zoom in around 2, 9, right, notice that I can zoom in and it looks like I have a line. This is local linearity. We can zoom in enough that we lose any curvature that the function had, and instead it starts looking like just a line, right? So this function has that local linearity, right? It would maybe look something like this, right, as we zoom in around it. Maybe it looks more like, kind of maybe lose that out a little bit, and it's like this. And then we zoom in a lot, it starts to look like, say, this. There's a little bit of curvature maybe to this thing, like that. But when we zoom in enough, it looks like we just have a line, right? It looks like a straight line with that 0.29 in the middle of that straight line. So we could do the same thing if I want to zoom in on either the x around 0.067. Oh, so we would say yes, right? So our function is differentiable at x is 2 because it exhibits this local linearity. So e to the x at 0.067. So let me get a function. Y equals e raised to the x. I don't even know what that point is. So let's just go 0.67 e to the 0.67. So there's our function. So again, if we just zoom in around this point, eventually I can zoom in enough that I lose the curvature of my exponential function, and it seems like we have just a line. So since we have this local linearity, we're really looking at the tangent line, in essence, we would say that e to the x would be differentiable at 0.067. I'll leave it up to you to draw this link. And then if we look at some other things that are going to have some problems, so cube root of x. So cube root of x is a function, looks like this. So if we zoom in around 0, 0, so y equals the cube root. You can do nth root in Desmos if you want. So cube root of x at the point 0, 0. That's about the origin. Right, so if I zoom in around this point, so if I zoom in enough, right, here's my local linear, like it looks like I have some local linearity, but the problem is that when I zoom in, this line that I have looks like a nice vertical line. And what's the slope of a vertical line? Well, it's undefined. So this function, it seems, does not have this local linearity, right? So it looks like when we zoom in, we're getting something that looks more and more and more like a vertical line. So it was fine for a little bit, just kind of gets stretched out like that. But we zoom in enough, looks like that. And then we zoom in enough, and all we see is basically that vertical line. So it seems like it does not have differentiability when x is equal to 0. It's differentiable everywhere else. So what we'd call this is a vertical line of tangency. So at the moment that we approach 0, our function is moving infinitely fast. The reason, if you take this derivative, right, so we saw this on the other page, if f of x is equal to the cube root of x, we took a derivative a page ago, we got 1 over 3 cube root of x squared. So when x is equal to 0, we gain this vertical asymptote in the denominator, right? That's what's causing that vertical line of tangency, where whoosh, derivative is shooting off towards infinity when x is approaching 0. Um, Two more. So if we did x to the 2/3 power, right, you may not know what that looks like. Right, so if I did x raised to the 2/3, we're going to get something like that. It looks like a bird if you were like 5 years old. So if we zoom in around 0, 0, we never lose this, like, it shows like the absolute value, right? We kind of have this like bird curvature thing going on here. right? But we never lose the fact that we have that kind of V shape if we zoom in more and more and more. So this is also an issue. This is what we call a cusp at x is equal to 0. So again, cusps don't have any. So cusps are a place where our function should be non-differentiable. And again, if you took a derivative of x to the 2/3, we're actually going to get 2/3 x to the negative 1/3, which is the same as 2 over 3 cube root of x. Again, we're seeing that this x is equal to 0. The denominator is causing a problem, where we're getting a vertical asymptote there, so we get kind of like an infinite discontinuity in our derivative. So to sum it all up and put a nice little bow on it, a continuous function is differentiable unless any of the following are true. It has a corner. And so corners look like these. It has a cusp. And so cusps look like birds when you're 5 years old. And it has a vertical line of tangency. Right? That's like this, where at some point you have an infinitely fast rate of change. Obviously, some other things could happen, but if we're not defined, obviously, we just don't even have a derivative, right? So if I say something like f of x equals 1 over x, f prime of x does not exist for x equals 0, just because x equals 0 isn't even in the domain of my function, right? So you can have undefined issues as well, which we'll see as we kind of like move on to some of the stuff in the next section. So what we have is, so if we have differentiable functions, any function that's differentiable means that I can take the derivative at any point. Differentiable functions are always continuous functions, right? So in essence, differentiability is a stronger property of the function than continuity, because I can have continuous functions like absolute values, x to the 2/3 cube of x, that are always continuous, but they're sometimes differentiable. So this is, again, something that's somewhat important, right? If we're differentiable, we're automatically continuous. But if we're continuous, we're not automatically differentiable. It works one way, but not the other. If there's any questions, feel free to let me know. If not, have a great break.